As pen testers, as hackers, cryptography is so much a part of our world, we need to have a handle on it and how it works. So let's take a look. Besides the people, the single most precious asset for an organization is its data. And data can be in one of three states. First, there's data at rest. This means it's just on storage media, not being accessed, it's not open, it's just sitting there. You could even have it on a thumb drive in your pocket walking around, but it's still at rest. Or we have data in transit, it's actively transmitted across the network. Or it's data in use. Data in use means it's loaded into memory and it is about to be processed on a CPU or has just been processed on a CPU. We can actually encrypt data in any of those states, but the two that we are most interested in right now is at rest and in transit. Cryptography is the process of taking just normal text or normal whatever and garbling it in a controlled fashion to make it unintelligible, and then ungarbling it so we can actually see it again. And this is to protect it, mostly to protect its confidentiality, but we can also protect its availability, and I'll get to that soon. So when data is encrypted, it can be safely stored because if someone steals the storage media, they make off with your removable drive or your thumb drive or the CD you've burned it on, or steal the hard drive out of your computer or something like that. Even if they steal it, in theory, they can't see it or view it or open it. Even if we transmit it across a network, if it's in encrypted format, assuming we did the encryption well, even if it's intercepted, they can't tell what it is. So cryptography, the whole goal is to protect confidentiality at the data level itself. Cryptography has several components. You have something that's unencrypted. We call it clear text, although it might not be text. It could be an image or voice or some media file or something. But for convenience, we still call it clear text. So you have this clear text or plain text, unencrypted. You then have something called an algorithm, also known as a cipher. That's a mathematical formula for scrambling that data. Now the problem is, if you only have the cipher, well, anyone can grab the cipher and unscramble, right? So we need to add something variable in that, and that's the key. A key is anything that can be reduced to a set of numbers, and that could be a swipe pattern, your facial geometry, a password, a bunch of numbers. Anything that can be reduced to ultimately a number set is the key. So you take the key and the algorithm. The key adds some unknowableness, okay? Because supposedly only you have the key, right? You have these two. You feed the plain text into them, and out comes this garbled cipher text. So that's the process. That's encryption. You want to decrypt? Then just go in reverse. Take the cipher text, same algorithm, same key. You want to decrypt? Then just go in reverse. Take the cipher text, same algorithm, same key, and out comes the plain text. That is the whole concept of cryptography. Now, there are all sorts of variations, but that's the basic thing. A cipher, as I had mentioned, is an algorithm. It's a mathematical formula for scrambling data. There are two basic types of ciphers. There's the block cipher and the stream cipher. Now, block cipher is for data at rest. I will break down whatever this document, file, image, video, whatever it is, into fixed size chunks. And I will encrypt each block. Sometimes I'll take a little bit of the output of one and feed it into the next one. Sometimes I won't, and there are variations of this. But I will encrypt it block at a time. This is really good for when you have big files that are just sitting there. Now, stream cipher is where we have data that's being transmitted one way or another, whether it's Wi-Fi or something. And as the data goes by, bit by bit, in a stream of bits, we will encrypt each bit. Now, because it's going in real time, you have to have a very fast way of encrypting it. And we'll talk about that in just a moment. Now, we have several ways of encryption. There is symmetric and asymmetric, and I'm going to get to hashing in just a moment. Symmetric encryption is where we use the same key to encrypt and decrypt. Symmetric, same key. It's also very fast, and we tend to use it with block ciphers. Asymmetric is where we have two keys. They're mathematically related. We use one to do the encryption and the other to do the decryption. We'll get to the implications of that in just a moment. Now, hashing is something different. Hashing in and of itself has no key. Now, there are ways to use a key in hashing later. With hashing, I'm just going to put whatever it is, file or like a network packet or something, I'm going to put it through an algorithm. And the algorithm is going to give me an output, not the whole thing encrypted, but instead it's going to give me sort of a representation, a signature that's only so long. So I could have a hash that, no matter how big or small this file or this data is, will give me, say, just 128 bits of output. And I change one little tiny thing in the original, and the hash comes out very different. But it's always a fixed size, no matter how big or how small. We use hashing to verify that the original, whatever it was, has not changed. And we'll talk more about these as we go along. Now, there is a method of encipherment called exclusive OR, and you need to understand this because it has implications when we are attacking cryptography, especially Wi-Fi. Exclusive OR is this mechanism. It's a Boolean logic, meaning yes, no, true, false, high, low, or in our case, 1, 0. It's true or false. It's 1 or 0. Now, here's how it goes. As the data is going by, we're going to have another stream of bits going right on top of it. And then we're going to kind of beat them together. And one by one, we're going to see the result for every single bit. And here's how it goes. If the two bits, if the data and the key stream have the same value, like if they're both 1s or they're both 0s, that's a false. But if they are different, like one is a 1 and the other is a 0, they are true. This is called exclusive OR. And we use it all the time in stream ciphers and certain kinds of cryptography. So take a look here. I have, say, just a streaming key that's being generated in real time, and I have data as well, and I just have this small amount here. If we were to understand how exclusive OR works, remember, if the two are the same, that's false. If two are different, that's true. And false means we get a 0, and true means we get a 1. So take a look. What would be the result? This XOR that. Well, the first two are the same, so it's a false, it's a 0. The next two, 0 and 1, are different, so it's a true. Doesn't that seem like backwards? But it is, right? So you have these two are different, so it is a true. The next two are also different, so it's a true. But the next two, both 1s, are a false. And the next two, both 0s, are false. And then two that are not the same, true. Two that are the same, false. Two that are not the same, true. And these things go by in this continuous real-time stream. So that's how we do it. We do the encipherment, the encryption, using exclusive OR. Not only does a stream cipher such as RC4, which was used by WEP and also WPA, the original WPA, not only do we use it for encryption in real time, but when we talk about things like polymorphic shellcode, in other words, malware, that too encrypts its code using XORing, exclusive OR, XOR. And then later, once we actually get our payload on the victim, we'll use XORing again to decrypt it. And now we've got our remote shell or whatever it is. So exclusive OR, we need to just be aware of this. And who knows, you might see a question that says, what would be the result of these two together? So remember, the XOR is kind of like the opposite of what you expect. What is it again? Two things that are the same, false. Two things that are different, true. A one-time pad is an encryption technique that cannot be cracked. Okay, so every message is encrypted with a different pre-shared key. And you and I need to know the pre-shared keys ahead of time. Okay, we need to know ahead of time. This means there's no pattern, because even if you figure out the key the first time, by the time you get to the next thing, our key is totally different. Now, you and I have to have identical copies of the keys, and if somebody gets compromised, the whole thing's in trouble. But assuming that no one's compromised, the keys are different every time, and it was very popular once upon a time. Now, don't mistake the one-time pad. Don't mistake this for the one-time password you might get on your phone. The one-time pad means you and I both know all the different keys, and we know they change every single message, and we agree upon it ahead of time. The one-time password is a multi-factor form of authentication where I'm using my phone, I go to a website, banking or something, put in a username and password, they're going to send me a code that I have no idea what it is, and that code is only good for just a few minutes, and I got to enter it, and if I don't, the code is useless and I got to ask for it again. That's a one-time password or one-time passcode, not to be mistaken for one-time pad. And then we have something called government access to keys, and this has been a struggle. We have government agencies, not only in the United States, but probably every country in the world, that demands from private industry that they give them copies of their secret keys, so that the government, if it intercepts transmissions or documents or files from criminals, they can decrypt it, they can decipher it. And of course, that raises all sorts of privacy issues and other things. But anyway, with government access to keys, the government wants to have enough copies of the various keys that the various vendors supply so that they can decrypt messages for law enforcement. They guarantee that they'll keep the keys secure. I wonder if that's true. And they guarantee they'll only use the keys if they get a court-issued warrant. So this is kind of like the usage. If they have the right to wiretap a phone, they get a warrant. Well, they'll get a warrant so that they can use these keys to decrypt. So this is our general overview of cryptography. And now, let's move on. So this is kind of like the usage. If they have the right to wiretap a phone, they get a warrant. Well, they'll get a warrant so that they can use these keys to decrypt. So this is our general overview of cryptography. And now, let's move on.